So let's keep working on our exercise. And in the previous video, we have come to the point where we have finished running this kernel transpose code. Right. And this kernel transport code, transpose code, transpose code is gonna take the non-zero kernel list as the input, right? And then it's gonna create a bunch of outputs that's gonna reside inside of the uh, kernel directory, and then subdirectory ktr, and it's gonna create a ktr dot ou followed by like 8 digits or something, and then all those files can be concatenated into like one single file that's gonna be named like ktr.ou. Can have different file names, whatever file names that's needed, right? And then a second output created by the KTR code is a count of the number of non-zeros per column, and this is also a binary output. That's called ANZ per code.bin. It's a binary output, right? And then for now, the LSQR code has to read a ASCII version of this binary file. So I have to convert this binary file to a ASCII file. And that's easily done. I have a very small C++ code that can do that. It's called zba.sh. So this zba binary, it's a sequential binary. It's going to read the inversion control file, and then the binary input, and then the ASCII output, right? So that's going to be the ASCII output file, and then this ASCII output file is going to store all the number of non-zeros every column. So it's a quite big file, right? It's a quite big file, and so if a column has no non-zeros, then it's a zero, right? But if it has a has non-zeros, then it's gonna give you the number of non-zeros for that particular column, and then followed by some kind of index that's gonna keep track of the total number of non-zeros so far for all the columns, right? And that's ZBA, right? So after KTR and the ZBA is done, what's gonna be the next step, right? The next step is to actually create the checkerboard pattern. So you basically need a model. You need a model that looks like a checkerboard, and this checkerboard pattern is created inside of this particular shell script, ckb checkerboard.sh, and it's going to call the sequential or serial binary executable ckb. Again, inversion control file, and then these are the frequencies or wave numbers in the x, y, and z dimensions. So for this particular experiment, the wave number or the frequency in the x dimension is 0, which means it doesn't change in the x dimension. And then it's going to have a frequency of 0.5. These frequencies are referenced with respect to the grid point, the grid number. Right? It's not referenced to meter or any kind of units. It's referenced to the number of grid points. Right? So that's the frequency. So inside of this CKB code, it's going to compute sine Ix times Fx multiplied with sine Iy times Fy multiplied with sine or cosine, sorry, it's not sine, it's cosine Fz multiplied with Iz, and Ix, Iy, and Iz are grid indexes, right? So it's not dependent upon the specific units, and you have to sort of make some adjustments to those frequencies in order for the checkerboard pattern to have the right checker size in each of the dimensions. And then the last number is going to be the amplitude of the perturbation. For now, it's just a 1, right? So the checkerboard is going to have is going to vary from between plus and minus 1, basically. If you want a bigger amplitude like 10 or something, or smaller amplitude like 1 to the 10 to the minus 3 power, sort of power, that kind of thing, then you can just change this number. So that's going to give you a checkerboard pattern that has a smaller variation amplitude. And then that's going to be the output, right? That's going to be the output file. It's again a binary output, right? It's a binary output. And then the file name, um, you can use any kind of file name, but the file name that I'm using here is just uh, recording the frequencies that are used as the input and also the amplitude as the input. And then ZYX is just telling myself this is permuted, right? So 210, that's the permutation. So Z is going to be the slowest direction and X is going to be the fastest direction. And then this particular file is stored inside of this KTR subdirectory, right? So that's all the CKB files that I have tried before. It's with different frequencies and different different amplitudes, I think, right? And also different kinds of permutation. Once the model or checkerboard model is created, the next step is to actually multiply this checkerboard model with the kernel matrix. And this is a matrix vector multiplication, right? So it's gonna be row-wise. We will have to access the kernel matrix row by row, basically. And this row by row calculation can be done quite quickly because all the rows of kernels are stored in the um, sparse format, right? Sparse compressed row format. So the calculations can be done in just a sequential code. So, but in the future, if the kernel matrix becomes indeed too big to carry out the calculation in a short amount of time using a sequential code, it's not difficult to actually change it to a parallel code. It's actually very easy. But for now, the problem is not big enough for me to actually take the trouble to change it to a parallel code yet. So I'm just doing a sequential code, and that's KXM, kernel multiply model, right? So, and then inside of this shell script, I'm calling the kernel multiply KXM executable binary, and then it's gonna take the non-zero kernel list as the input, right? And then the checkerboard model that we created using CKB code, and then the output. That's the right-hand side. That's the fake measurements. That's the synthetic measurements, basically, right? Um, and then when you do the checkerboard test, you use these synthetic measurements as the right-hand side, and then try to solve for the checkerboard, right? The recovered model is not going to be exactly look like the input checkerboard, but the degree of recovery or the extent of recovery basically tells us the coverage of the model and the resolving power of the inversion, basically, right? And this is a sequential code. KXM is a sequential code, so it's gonna run and then create this particular output. And this particular output is called, the file name is called B. That's the right hand side, and then followed by the frequency of the checkerboard pattern, and then the amplitude of the checkerboard pattern, and then it's an ASCII file, it's a text file, and then here I'm because the kernels have been scaled with respect to depths, following the power law of the power law, right? The scaling is proportional to the depth to the power of 0.5, right? So the file name of B actually reflects that, right? And that's gonna be the right hand side, right? That's gonna be the right hand side of the linear system. Um, and then we still have one more step that we need to actually carry out in order to actually before we run the LSQR code, which is actually generating the damping matrix for the entire linear system, right? Did I miss anything? Let me just take a look. No, I don't think so. So how do we actually generate the damping matrix, right? Um, Again, we have a shell script that's gonna call a binary. It's a sequential binary, but this time we have to remember to make a directory because all the outputs of the damping matrix are gonna be stored inside of this particular subdirectory inside of this KTR subdirectory, right? So the damping matrix has like two components. One is amplitude damping, which basically suppresses the L2 norm of the model. You don't want the L2 norm of the normal to be like outrageously big. Right? And then another one is the smoothing. You want damp the gradient or the second order gradient. Actually, it's a Laplacian of the model. So you don't want the model to be too rough. You want the model to be uh, smooth enough, right? And then for this particular experiment, the amplitude damping is 1, and then the smoothness damping is also 1. And then because it's permuted, so Z is going to be the slowest direction. And then once you have created this directory, you can use the DMP code, damping. DMP represents damping. This is again a binary, sequential binary, and then it's going to take the input uh, control file of the inverter, and then the directory that you just created, and then followed by 7 numbers. The first number is going to be A, amplitude damping. Amplitude damping is like a constant. It doesn't actually vary with directions. And then followed by 1, 2, 3, 4, 5, 6 numbers. And these 6 numbers actually specify the Laplacian damping in each of the directions, right? So basically you have to specify the direction of x, x, y, y, z, z, right? X, x, y, y, z, z, and then x, y, x, z, and y, z, that kind of thing. So in order for the Laplacian damping to account for all the different kind of combinations of derivatives, that kind of thing. And then the last 3 numbers is actually the permutation. So 2, 1, 0, z is going to be the slowest, x is going to be the fastest direction. So once you have finished executing this piece of code, you're going to see these particular directories, and inside of those directories are going to be binary outputs that's going to store all the damping information, right? Damping is stored as a column-wise, and row-wise damping information. These files are not really that big. It's because it's very very sparse. It's primarily just zeros, right? And then all the non-zeros are kind of sort of clustered around the diagonal. So the total number of non-zeros are really not that many. So these files are quite small, right? But the transposed kernel output could be quite big. For this particular exercise, um, it's like it varies, right? It varies because I have scaling on the kernel. So if the scaling is kind of big enough, it could make the small kernels at depths quite big, and then the total number of non-zeros for the kernel files are going to be larger. So that's going to give you a larger kernel matrix. This is gigabytes, right? And then for the experiments, for the plots that I was showing you at the beginning of the first video, it was created using this particular kernel matrix that has a kernel scaling that's z to the power of 0.5. And then we are pretty much ready to run the ALSKR code, right? The ALSKR code was created by Li Chang Wang and his group and his collaborators, right? And his students, some of his students has graduated a long time ago. His collaborators are still working, but not on our project anymore, but working on some other things. So this ALSKR code is not maintained anymore. So the version that I'm running is still identical to the one that Henry used in his thesis. So this code is like 4 or 5 years old, without any kind of update, without any kind of improvements, right? So a few things, right? That's the parallel binary, right? And then the directory for storing all the kernel matrix, and then also the right hand side and also the damping subdirectory, the subdirectory for storing all the damping matrix, that kind of thing. And then that's the assembled kernel matrix binary file. That's the 85 gigabyte file that I was showing you. And then the non-zero information file that was converted from binary to ASCII using ZBA, that binary. And then uh, the damping matrix that has to be referenced to the subdirectory that's inside of this particular working directory. Um, dampf by call, right? Um, dampf means it's a row matrix, and then by call is a column matrix. Damp I, that's the information, right? The information for the row matrix, and then by underscore I by underscore by call, that's damping by column, information by damping, and then the total number of iterations I'm doing is like 10,000. Row D, that's the damping row, the total number of rows for damping matrix. How I actually got this number, right? But when I was running the damping, so if I run dmp.sh, um, yeah. So if I run dmp.sh, right? So it's gonna tell you what's the total number of damping rows, right? And this number is supposed to be copied over manually to the job script for LSQR. Again, this is not a very good setup, right? For the user of the code, I have to automate this part. It cannot be sort of always like this kind of thing. Uh, um, it has to be automated. Maybe I should write this information into a particular file and then let the LSQR code to read that file or something. Um, but for now, let's not worry too much about that. And then the total number of columns, that's the total number of model parameters, right? Again, it's numbers that are copy pasted from outside of the code. It's the total number of grid points, or recording grid points in X, Y, and Z, those directions, multiply them together, right? But that's for just one model parameter. For VS, right? If you have like a multiple model parameters like VP and VS, then this number has to be multiplied by 2. Right? If you have like 3 model parameters, including like density or something, then it has to be multiplied by 3, right? And then that's the right hand side, the file for storing the right hand side. And then the total number of rows inside of this particular file, right? So this is actually a C code. It's not really a C++ code. So it has to read all those kind of inputs in order to actually construct or allocate memory inside of it. So it cannot really just maybe not. It's not cannot. It's just when the code was written, it was not written in a way that's for automating lots of those kind of input parameters, right? And then for this particular exercise, each LSQR run takes about 10 to 15 minutes, right? So depending upon how big the kernel matrix actually is, so it's going to take like 10 to 15 minutes. And after the run is finished, it's going to create some output files. One is the result.txt file, and the other one is actually the model, the inverted model, right? And for this exercise, I was storing all the results inside of results1. And then inside of results1, I have a bunch of subdirectories, right? And then inside of each subdirectory is actually the result for one LSQR run, right? For now I have done like 10 different runs, and each of the runs are actually using different kinds of parameters that I was trying out to find out what's actually the results, right? So at the beginning I was just trying out different smoothing parameters and try to see which one is actually a suitable smoothness damping parameter, right? So I found that A1S1 to be actually giving me the best result. And then all the rest of the simulations are sticking with A1S1. And then using different kinds of combinations of using different permutations, I was trying out different permutations, right? Turns out ZYX actually runs slower than XYZ actually. That's kind of surprising. For some reason, I will have to look into later, right? One of the things I didn't do for the LSQL code is actually load balancing. So for now, the number of non-zeros or the total number of columns are evenly distributed across all the processes, MPI processes. So it's not exactly an ideal load balance. It's not very well load balanced across different processes. So maybe if I do the load balancing stuff, then the advantage of using a correct or a different permutation could show up using different runs. Um, and then I was trying different kind of scaling, kernel scaling, to see if I can actually recover the checkerboard pattern at larger depths, right? Uh, Turns out 0.5 looks better, right? Uh, and then the 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 output files. This is actually a text file, right? So all I have to do is to actually take a look at the text file. Um, it's gonna have it's gonna have like a 10,000 iterations because we specify 10,000 iterations for the LSQL run. And then the numbers are actually showing um, the different columns are actually showing you condition numbers and the cost function, how it's actually decreasing. So the first column is actually the iteration number. The second column is actually um, the value of the model at one of the grid points. It's actually x1, and then function is actually the cost function. It's supposed to decrease actually. So it starts with like a 2,000 something, and then ended up with like 40 point something. Right, so that's a substantial decrease in the substantial reduction in the cost function. That's something that we would like to see if the model is actually correct. And then the rest of the columns are kind of related to the different norm or condition numbers of the matrix and its transpose. And you don't want the condition numbers to be huge. The huge condition numbers is like a bad thing, but at least after like 10,000 iterations, the condition numbers are not really that big. And then the actual inverted model is actually stored inside of the uh, uh, inside of this binary output, right? And this binary output is just a flat binary vector. It doesn't have any kind of metadata stored inside of it. The number of floats. The number of floats it's stored inside in terms of float 32. The number of floats that's like 4 bytes, right? 4 bytes. The number of floats is exactly the same as the number of model parameters. And if we want to sort of make a plot of it, we have to actually transfer it to local machine and then use MATLAB to actually make a plot of it. So that's the script that I used for making the cross-section plots that I was showing you at the beginning of the first video, right? So this script has to actually we have to use some MATLAB scripts that's provided by SW4 in order to actually read the mesh. So these read image functions are actually coming from the tools subdirectory of SW4. And then this read image thing is actually using a file name as its input, and the file name is actually those grid inputs, those image outputs that I was showing you. Those files actually, those files created by SW4, and you can actually specify those outputs inside of the input file for the SW4, and here it's images, right? These lines of code actually controls the output of those files that's going to be read by MATLAB later on when we make plots, right? You want that's the map view plots. We are looking at the topography. We want to know the latitude and longitude, and we want to look at the shear wave velocity at the 0 depths. And then cross sections, we want to look at the cross section at x equals to 88 meter. This is in terms of meter actually. X equals to 135 meter, 183 meter, that kind of thing. And then material properties, the P and S at 135 meter, x equals to 135 meter cross section. So those files will have to be transferred from to the local machine for MATLAB to read. It's gonna read those grids, and then because we have like two subgrids, right? So we have to read like twice for each of the file, right? Uh, in order to actually get the two subgrids, and then the two subgrids has to be assembled together by using these lines of code. Once you got the unified grid, you can decimate it. Decimate it based upon the decimation rate used in your inversion. That's like 5 meters or 5 grid points in the x and y direction, and 1 meter in the z direction, right? And then here it's actually reading the output, the binary output of the LSQL code, right? So it's not really that hard to read because it's just a flat binary. Use freader to read it, and then my and mx are three-dimensional matrices by reshaping the one-dimensional flat matrix. So x, y, and z, right? So MATLAB has this kind of convention. Fast directions has to come first. Slow directions comes later, right? So our output has been permuted. So x direction is like um, the the fastest direction, and z direction is the slowest direction. So that's gonna be the correct ordering of the reshape command. And then once the mx and my are created, you can just we can just do a p-color plot, right? And then um, set the coordinates right. When we do the p-color plot, the coordinate in the two directions, x and y directions, has to actually come from the grid locations, because the gy and gx grid actually accounts for topography. Otherwise, it's just going to be flat topography. So those gy and gz, those files generated by S34 has the topography information inside of them. Yeah, so that's pretty much the entire exercise. This code is not yet kind of as mature as AWP code and also the DG code to some degree, right? Uh, but uh, but at least it's a working version. The entire workflow is like working now, and if there's any kind of problems, we can try to actually fix it. Uh, in a realistic inversion, the actual measurements will actually have to come from the actual data and the actual synthetic sound environments. What's actually missing out in this sequence of videos is actually the procedure for computing or measuring the misfits, the waveform misfits, right? And there's another code for doing that. Um, but let me end this video now, and we'll talk about other things in later videos.